We got off to a great start in this class with the process of science, and I've seen from the assignments that you handed in that many of you have an expanded view of the nature of science and know that it goes much beyond the experimental method that many of you were introduced to in high school or other science courses. Now we're going to turn our attention to biological chemistry, which is the subject of Chapter 2. So, why are we studying chemistry? This is a biology class after all. Well, we're interested in understanding how living organisms function, and it turns out that the same chemical elements that are found in non-living objects are also found in living organisms. And because of this, living organisms also obey the universal laws of chemistry and physics. This comprises what's known as a mechanistic view of life. It's very different to what was held in the 19th century, where people actually thought there was something called a vital force that was very different from what was found in inanimate objects, and that it was responsible for life. So, for example, it was not well understood that a carbon atom in a chair is the same as the kind of carbon atom that's found in a living organism. Over time, a new view, this mechanistic view, came into favor, supported by a lot of scientific evidence, and that has led to great advances in biology, medicine, and agriculture. So, understanding chemistry then helps us understand biology. So, living organisms are made up of a substance called matter. By the way, this is the same stuff that non-living things are made of. But this matter consists of smaller particles that are called atoms. Atoms contain at least one proton and at least one electron. Protons are found in the nucleus, and they're colored red in the diagram here on the bottom of the screen. And electrons are found outside of the nucleus. They have a negative charge and they travel, as you can see in this animation over here. And the area in which the electrons travel is sometimes referred to as an electron cloud. And although from this animation it does appear that the electrons are traveling in a somewhat disordered fashion, they're actually traveling at fixed distances from the nucleus and along a fairly regular path. So in addition to protons and electrons, all atoms except hydrogen have another kind of particle in the nucleus, which is called the neutron. Now, neutrons and protons are of equal mass. They are both equal to a mass of 1 Dalton. The difference between them being simply that a proton has a positive charge and a neutron does not have a charge. Now, the number of protons in an atom is extremely important. In fact, it determines what kind of element a particular atom comprises. So the number of protons is definitive and it does not change. And so the number of protons then is referred to as the atomic number. Now, because a proton has a charge of +1 and an electron has an equal but opposite charge of -1, when the number of protons in an atom is equal to the number of electrons in an atom, then that atom is electrically neutral. So this is what's called the periodic table of the elements. It shows all of the elements listed in order of atomic number, starting from hydrogen all the way at the top here. It's read usually from left to right. For our purposes, we're concerned with the elements that are highlighted in yellow: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. And believe it or not, even though there are many elements that are shown in this table, it's those 6 that are highlighted in yellow that make up 98% of the mass of most living organisms. That's pretty astounding, and in a few minutes we'll discuss some of the reasons why these particular molecules are so special. Now, when you're reading a periodic table, the number at the top refers to the atomic number or number of protons. The number at the bottom is the atomic mass. This includes the number of protons plus the number of neutrons. So let's turn our attention now to electrons. You'll recall from this diagram that we looked at earlier that I mentioned that even though those electrons appear to be traveling in a somewhat disorganized fashion, that they were actually traveling at fixed distances and along certain paths from the nucleus. These fixed distances are what we refer to as electron shells. In the diagram on the right, which is called the Bohr model of an atom, these shells are represented by the solid gray lines that move outward from the nucleus, which is shown in red. In the diagram on the left, the shells are indicated by the blue and purple spheres. I really like this diagram on the left because it really shows you that even though we draw these electron shells as a sphere, that what's really happening is that within each of those shells, electrons are traveling on unique paths. These paths are what we refer to as an orbital. And at most, 2 electrons can occupy each of these orbitals. So for most of the atoms that are important in terms of living organisms, they are the most stable when their outermost electron shell contains 8 electrons. And this is what we refer to as the octet rule. There are a couple of noted exceptions to this octet rule, particularly hydrogen and helium, which only have 1 valence shell and therefore are most stable with 2. And if you're not clear about this, you can look at this Bohr diagram and it shows quite clearly that the innermost valence shell can contain at most only 2 electrons. So this octet rule is very important when we're thinking about the chemical reactivity of an atom. It turns out that atoms that actually have less than 8 electrons in their outermost shell will actually react with other atoms in order to become stable. And they'll do this in a couple of ways: through the sharing of electrons or the complete transfer of electrons. In both cases, this is done so that the outermost shell actually has a complete set of electrons. So then, electrons determine the chemical reactivity of atoms. And what this really means is it determines the type of chemical bonds different atoms can form. So a chemical bond is simply an attractive force that holds 2 atoms together. And there's one other term I want you to be familiar with, and this is the term molecule. So if you have 2 or more atoms of the same element bonded together, this is called a molecule. If the atoms are different, we call that a compound. So at the bottom of this screen, this is showing an example of a molecule, and this is hydrogen gas. So those red dots indicate the nucleus of those hydrogen atoms. The black dots are the electrons that are orbiting the nucleus. Now, hydrogen is one of these atoms that is most stable with 2 electrons in its outermost shell. And for this pair of hydrogen atoms, this has been achieved by sharing electrons. And you'll notice that both of these electrons are spending time around each one of the nuclei. So this type of arrangement where atoms share electrons is referred to as a covalent bond. These are extremely strong bonds, and they're very important in biological molecules. You'll see later on in the semester that covalent bonds are important both in energy transfer, because they can store much energy within them and also release much energy when they are broken. They also hold macromolecules together. Covalent bonds are what we call directional. They don't flex. And so the bond that actually forms is a balance between the attractive forces that each nucleus places on the electron of the other atom. And you can see this attraction of the electron in this middle diagram here. So these atoms shown at the top have not yet formed a chemical bond. The nucleus is shown in the middle with the dark black. The electrons are represented by that fuzzy blue cloud. As these 2 atoms come into contact with one another, these are hydrogen atoms. They each have 1 electron, 1 lone electron in their outermost shell. The positively charged nucleus of the other atom attracts that electron, and it attracts it enough eventually where that electron starts to spend time around the other nucleus as well. So there's this attractive force exerted on electrons, but the bond distances in covalent bonds are quite standard. They do not vary, and the reason for that is that the nuclei, which are positively charged, actually repel each other. This results in a fixed distance for all covalent bonds, so they have a standard bond length. And what I mean here is not that every covalent bond has the same length. I mean, in this case, every covalent bond between a hydrogen and hydrogen would have the same length. So in the case of this covalent bond between hydrogen atoms, the electrons are spending equal time around the nucleus. And they're doing that because the attractive force that those nuclei are exerting on those electrons are exactly equal. Both of those hydrogen atoms have one proton each in them. They have an equal charge and equally attract electrons. Electrons then spend equal amounts of time around the nucleus. So covalent bonds do form between atoms of different types, and that can actually lead to unequal electron sharing. To understand this concept of unequal electron sharing, we first have to discuss this concept of electronegativity. And electronegativity is the attractive force an atom exerts on an electron. We just saw an example of that. This is a table from your textbook, and it shows you some electronegativities of some various elements, from oxygen to potassium. The higher the number, the stronger the attractive force that particular nucleus exerts on an electron. And I encourage you to go back and look at the periodic table and see if you can make sense, for example, of why the electronegativity of oxygen is so much higher than that of, say, hydrogen. So let's take a look at an example of what happens when you have a covalent bond that forms between two atoms with different electronegativity values. In this case, we're going to consider hydrogen and oxygen. And you'll recall from the last slide that oxygen has an electronegativity of 3.5, whereas hydrogen has an electronegativity of 2.1. What this means is that oxygen's a bit greedy when it comes to its electrons. So one of the things that happens when covalent bonds form between atoms that have different electronegativities is that it causes the molecule to have a property known as polarity. And this is where you have different parts of the molecule that actually have a partial electric charge. So let's take a look at how this happens in a very important molecule to biology, which is water. And of course, you know the formula for water is H2O, which means that water consists of two hydrogen atoms bound to one oxygen atom. And if you look at the animation down here on the bottom of your screen, it's showing you what's happening with the electrons when these covalent bonds form in water. So oxygen is much more electronegative than the hydrogen atoms. So that means it exerts a stronger pull on those electrons. As a result, the electrons spend a larger amount of time around the oxygen atom than they do around the hydrogen atom. When they do that, that really unmasks the charge of the proton that's in the hydrogen atom. And so the hydrogen atom then has a partial positive charge, which is indicated by the Greek letter delta here. Any kind of compound that has this partial charge is what we call a polar compound. So the difference then between a polar covalent bond and a nonpolar covalent bond is whether or not the electrons are being shared equally. In the case of the two hydrogen atoms that we considered earlier, that is a nonpolar covalent bond. Those hydrogen atoms equally share those electrons. In the case of water, that would form what's called a polar bond. Now I just want to stress here before we move on that even though we always use water for this example, that it's very possible for hydrogen bonds to form in other molecules as well. For example, we find that hydrogen bonds can form between two different parts of large molecules, like a protein. in addition to the sharing of electrons, sometimes atoms form a chemical bond which is the result of a complete transfer of electrons. And this is what's referred to as an ionic bond. These are not as strong as covalent bonds. And I'm going to talk about the mechanism for these bonds here in just a moment. But basically what happens is that the transfer of electrons results in the formation of an ion. This is an atom with an electric charge. Opposites attract in the case of ions, and in an ionic bond there is an attraction between a positive atom and a negative atom that have become so because of the transfer of electrons. So let's take a look at what we're talking about here. So this animation is showing the formation of an ionic bond between sodium and chloride. So chloride has 7 electrons in its outermost shell, and sodium only has 1. Chlorine is also quite a bit more electronegative than sodium, so it actually manages to pull the electron completely away from sodium. When it does that, the sodium ends up with a net positive charge, and if you'll look at this really quickly, you'll see that right after the electron leaves the sodium atom, right now there's a positive charge on that sodium atom, and because the chlorine atom now has an extra electron, it has a net negative charge. So the ionic bond is forming as a result of the attraction of this positive ion, which we call a cation, to the negative ion, which is called an anion. So you might have noticed on this slide that it mentioned that ionic bonds are fairly weak. They're stronger than hydrogen bonds, however, but weaker than covalent bonds. One of the hallmarks of an ionic bond is that compounds that are held together by these kinds of bonds tend to be very hydrophilic. And what this term means is that they readily form hydrogen bonds with water. So this slide is showing an example of what happens when table salt or sodium chloride is put into water. Now you'll recall that water is what we described as a polar molecule, which means it has regions of partial positive charge and partial negative charge. And if you put any kind of compound that is held together by an ionic bond into water, what happens is that those partial charges on the water actually will readily form bonds with the ions that make up the ionic compound. So let's look at this example of our table salt. The large green represents the chloride ions. The small blue represents the sodium ions, which are positively charged, and the moment that this salt gets into water, these water molecules start to surround that crystal structure of the salt, and you'll see that the negative parts of the water orient themselves around the sodium atoms, and that the positive parts of the water molecules orient themselves around the chloride ions. And this has the net effect of causing this crystal structure to dissolve, and this is exactly the reason why salt dissolves in water. So again, we call this property hydrophilic, and many substances are hydrophilic, and that's a good thing for us since our bodies are made of a very large percentage of water. Now, there are molecules that do not readily form hydrogen bonds with water. They are what are considered hydrophobic molecules. And what's interesting is some people see this term and they really think that being hydrophobic means it pushes water away. And that's actually not what happens in the case of hydrophobic molecules. What actually happens is that the water actually forces the hydrophobic groups together to actually minimize the breakage of hydrogen bonds. And you've seen this before if you've ever dropped oil on the surface of water and you've seen how the oil sticks together. Water is actually a very special molecule, and not just because of these hydrophilic and hydrophobic characteristics of some of the compounds that we've discussed today, but it really results from this hydrogen bonding that occurs in liquid water. But the degree of this hydrogen bonding that occurs in liquid water is quite extraordinary, and it imparts some very unique characteristics to water that, frankly, if water did not have life on Earth would probably not be possible. This is one of the reasons why scientists who are looking for extraterrestrial life look for the presence of water. So let's see why water is such an important compound. First of all, water has what's called a very high specific heat. And what this means is water can actually absorb quite a bit of energy before it actually changes temperature. So think about this. You've probably seen how long it takes water to boil on a stove. I know, it always seems like it's longer when you're watching it. But we also see this in environmental conditions. So, for example, you might see a more mild climate near a beach or a lake because of the amount of heat that that water body can absorb before it actually changes temperature. This is also really good for us because it means that our bodies don't tend to heat up very rapidly, and it makes us somewhat resistant to temperature changes. Water also has what's called a high heat of vaporization. And this refers to the amount of energy that it takes to convert liquid water into a gas, basically to get it right at the boiling point. And this chart just compares water to some other substances. And so I want to call your attention to this column on the far right-hand side of the table. What's really astounding is that if you look at the heat of vaporization of some of these compounds, for example, if you look at ethyl alcohol, its heat of vaporization is 854, whereas that of liquid water is just over 2,000. What's really remarkable about this is the only other substances on this table which approach a heat of vaporization that high are actually metals, silver and copper, which is much, much higher. So why is it that it's so hard to get water to boil? It's because of those hydrogen bonds, which tend to make those water molecules very sticky when they're in a liquid state. Another very important property of water is that it has a very high cohesive quality, meaning that water molecules stick together. This is really important for helping see that water gets transported all the way up to the tops of tall trees, and it also provides the water surface tension that you've seen on the surfaces of lakes and ponds, which is very important to certain organisms. An example of this is the basilisk, what's also known as the Jesus lizard.
Some young Costa Rican basilisk lizards are looking for food.
Aren't those little guys really cool? Who can't love a lizard that can run on water?